Gillian, look over there. It's a second-order linear ordinary differential equation. It sure is, Fred, but what's it doing? It looks like it's, gosh, Gillian, it's transforming. Wowza, second-order linear ordinary differential equation. You just turned into a 2x2 system of first-order ordinary differential equations. However did you do it? But a trifle, dear Gillian. I first let y prime be equal to a new variable x, and substituted it back in. I can even put myself in matrix vector notation, if that makes things clearer. Just a moment. Here I am. Wow, that's amazing. But how can you be solved when you're like that? Aha! To explain that, Fred, we'll need to go deep into the legends of linear algebra. Once upon a time, there was a matrix named A. She was a full matrix and was living peacefully until one day a strange figure came up to her. Hello, A. I am your eigenvalue, lambda 1. My eigenvalue? Why, yes. Together with my brother lambda 2, I described the core of your identity. In fact, I am one of your diagonals. But even with your brother, you're just two scalars. However can you describe me, a full matrix? Well, A, you can undergo row reduction and still explain your essential true self, can't you? As long as the information about the row reduction has been maintained? Well, I suppose so. Well, lambda 2 and I are just the culmination of that process. Even when you've been totally decoupled, you express the same facts, don't you? Given the decoupling information? That's the eigenvectors. So, you can use us to solve any problems you might get into. Great, but if I need to find you in lambda 2, how can I find you? Unfortunately, neither of us has a phone, but there is a way you can find us. Remember that we fulfill the problem a times x equals lambda times x from certain special x's, eigenvectors. Now, that's the same as solving the problem a minus lambda I x equals to 0. So now, you're certainly not 0, and neither are your eigenvectors, so all you need to do is find out when the determinant of that other matrix, a minus lambda I, is equal to 0. Then, lambda 2 and I will be there. Oh, thanks, lambda 1. If I get into any problems, I'll be sure to call on you. But before you go, I want you to meet your eigenvectors. Oh, here comes C1 now. Hello, A! I am your eigenvector. As am I, your eigenvector. Oh, where's number 2? Oh, and I'm the other eigenvalue. Ah, we are your eigenvectors. We are the vectors which you map to multiples of ourselves, lambda 1 and lambda 2 multiples to be exact. Happy, happy eigendance, even though we have no pets, we can describe problems now to solve the equations we know how. So, ODE, it sounds like you need to find your eigenvalues and eigenvectors to be solved. That's right, Fred. Each of my eigenvector pairs is one of my linearly independent solutions. If I can transform myself into a diagonal matrix, then component-wise exponentiation will be the same as matrix exponentiation. Someday, when I'm all solved, I'll look like this. Oh, ODE, that would be lovely. But ODE, what will your solutions look like? I mean, what will they really look like?
Well, Fred, that depends a whole lot on my eigenvalues and eigenvectors. They really have most of the say. But I can show you both some examples from your own lives. Ooh, fancy. Once, long ago, Fred and Jill were in love. Their feelings for each other could be described as a 2x2 system with a matrix of coefficients. The change in Fred's affection for Gillian and the change in Gillian's affection for Fred are related respectively to their existing levels of affection for one another by these constants. If both eigenvalues of the matrix are real and positive, their feelings for one another will shoot out towards a very far direction, either towards mutual love or absolute hatred. The directions that separate these trajectories are, in fact, the slopes of the eigenvectors. Real and negative eigenvalues result in all of their affections ultimately going towards zero or mutual apathy, which is probably what happened because, frankly, they're just friends these days. If one eigenvalue is positive and one negative of that matrix, a so-called saddle shape would result. This means that on one side of the stable manifold, all of their feelings would go towards absolute mutual bliss, whereas on the other side, if their initial conditions started out somewhere else, they would hate one another terribly after an infinite time. For complex conjugate eigenvalues, such as these, we'll see a spiraling sort of effect, which the solutions will be described by sines and cosines. For a complex eigenvalue with a positive real part, the solutions will spiral outwards towards ever more passionate mood swings, whereas for a complex conjugate eigenvalues with a negative real part, their feelings will spiral inwards, eventually reaching zero. On the other hand, the borderline case is of a purely imaginary eigenvalue, which will put them in permanent cycles, sometimes loving one another, sometimes hating one another eternally. But at least they'll like one another a quarter of the time. For repeated eigenvalues, sometimes a linearly independent eigenvector can be found for the same eigenvalue. Otherwise, we must find a generalized eigenvector so that the second solution to the differential equation will look something like this, where eta is a vector which solves the matrix A minus lambda I times eta is equal to psi, the first eigenvector. Okay, so that's all well and good, but I'd just like to briefly give an example of something that is slightly less personally embarrassing to me. Okay, so if you've got the position of a mass on a spring on the x-axis, and then you've got its velocity on the y-axis like this. You see, you start over here, and it's like it has a low negative position, but it has zero velocity, but then when it has zero position, it has like an upward velocity like that, and it just goes round and round and round, and this is what would happen if you had a mass on a spring with no friction and no damping and nothing like that, and no forcing, so it would just have constant energy the whole time. That's just like those ones where it's like x double prime minus something x is equal to 0, so those have imaginary eigenvalues. Yeah, just wanted you to know that. Thanks. Bye, friend.